All right, everyone, hello and welcome to this month's PCAST talk. So we are going to have a great talk today on protostellar disks. Before we get into that, just a few updates on things. So hopefully you know our Geo Book Volume 2 is now accepting submissions, so we're excited to hear science cases from the community as to what you would like to do with PRIMA. So you can visit the webpage to learn more and check out especially the exposure time calculator, as well as watch recordings of last month's community webinar that give you information on instrument capabilities. Our working groups have also launched and are starting to meet. This is all being coordinated on Slack. If you're not on the Slack or haven't signed up, there's still time to sign up. So we have working groups across wide areas of science led by really wonderful folks from the community. So thanks to all of them for doing this work. And last, I wanted to mention that we are holding a hybrid working meeting on PRIMA and the future of far infrared science. This will be on the Caltech campus, hosted by IPAC, May 19th through 21st. So you can visit the IPAC webpage to register and to get more information. Registration will close, is free, first of all, so registration is free, and it closes this Friday. And again, this is fully hybrid, so you can attend in person or join virtually. So upcoming, we have more talks in the coming months. So we'll have Joachim Basselmans talking about detectors and Deshika Narayanan talking about some precursor work for simulations. But today, of course, we have Coco Zhang visiting us from the University of Wisconsin, who's going to be telling us about gas evolution in protoplanetary disks. So thank you, Coco.
Yeah, thanks, Bessie, for the introduction. Let me share my slide. Okay, can you see the slides?
Looks great, thank you.
Okay, great. Yeah, so today I want to talk about some latest insight about gas evolution in protoplanetary disks. This is an ALMA large program, but the science is coherently related to PRIMA science. So one of the fundamental questions in astrophysics is trying to understand how planets form. We now know planetary systems, they are byproduct of star formation. So inside the molecular cloud, some part of it gets very dense and cold and start to collapse. And due to the angular momentum conservation, we naturally have an accretion disk around the young-born star. And initially, for the first 1 million years, there may still be a lot of envelope materials around. After 1 million years, we have a pre-main sequence stars with a protoplanetary disk. And this disk stage is really a critical stage for planet formation because at this stage is micron-sized particles have to grow into millimeter-sized pebbles and to kilometer-sized planetesimals and eventually to planetary cores. In particular, if we want to have any gas giants, it really has to happen within this stage when the gas is still in those disks. So gas is the dominant mass constitute of those protoplanetary disks. Initially, 99% of the mass we expect in the gas. So it really has an important role in almost every step of planet formation. So initially, the gas regulates the dust dynamics. So how dust particles, they grow to pebbles, planetesimals, and planetary cores really depends on the local gas to dust ratio. So we have to understand the gas distribution across those disks. And later stage, the gas provides the reservoir for the gaseous envelope of forming planets. Whether we ended up with a gas giant, ice giant, or mini Neptunes, or super Earth, it really fundamentally related to how much gas are available during the accretion stage. And finally, after the planet is formed, it may migrate across the disk. It can migrate inwards or outwards, and the direction and speed also coherently related to the gas surface density distribution. So for those, every step of planet formation, we require an understanding about the gas distribution in those disks. Yeah, anyway, our understanding of what drives the gas evolution in protoplanetary disk, it's related to the transport or remove of angular momentum in the disk. So what mechanism drive those angular momentum transport and removal is the key thing. So there have been two leading theories to explain the angular momentum transport. Traditionally, there is the turbulent viscosity idea. So most of the materials in the disk would lose their angular momentum, and these materials would drift inwards towards the star. And a small amount of material, they instead will gain angular momentum and they spread out. So those transport process happens due to the turbulent viscosity in disks. Another leading theory is it's called the Magneto-hydrodynamic disk wind idea. So instead of redistribute angular momentum within the disk material itself, in this scenario, so the disk materials close to the surface, they can get accelerated along magnetic field line. And when those materials leave the disk, it will remove angular momentum from the disk, and therefore the disk materials also drift inwards. So we don't still know whether any of those are indeed the dominant evolution mechanism in disk. If so, which one has played a primary role? So there have been a lot of effort trying to identify the driving mechanism of angular momentum transport. So there have been generally two approaches. One is to study individual disks, to look at the signature predicted by the different mechanisms. For example, to look at turbulence level in disks. But so far, the turbulence measurement have been extremely difficult. Most of the effort turned out to be upper limits, and only a couple of disks we have a constraint of turbulence level. Similarly, we have been trying really hard to look at signature of disk wind, but the results also are inconclusive. Instead of individual view, another approach we often try is a population view. This is similar to study HR diagram with stellar evolution. So you look at the disk as a population to say how the mass evolve over with age, how the disk size evolve with age, how the accretion rate, and how those evolution depend on the stellar mass. But in this approach, you require a population rather than a couple of individual disks, because you wanted to say a large statistically how the things evolve. So far, those population studies are mostly limited to the dust component. So mostly the mass and the size evolution. We have a large population of few hundreds of disks. We have mass and size constraints. Even if it's from those limited views, not from the gas itself, from the dust, we already know protoplanetary disk evolve over time. So there are a couple of tracers showing the evolution. One is the infrared axis. So from the classic identification of protoplanetary disk, you have the photosphere, and you have near and mid IR axis indicating dusty materials around the young star. So from the near IR axis, 2 decades ago, there have been studies showing so the fraction of young stars for giving star forming region, the stars with infrared axis, they decrease with time. It seems for the young stellar forming regions, so they have a high fraction of this young stars with disks, while when you go to older and older regions, so 5 to 10 million years, you have like 10% of the stars have infrared axis. So this indicates evolution of disk fraction. Over the past decade, particularly survey of dust mass with ALMA suggests for a few million year protoplanetary disk, their dust disk mass has a wide spread, but the median value are similar. But when you move to the 5 to 10 million year disk, like the upper score region, so the medium dust disk mass really decreases compared to the younger regions. So those are all indication of protoplanetary disk involved on the timescale of a few million years. But so far, those are dust tracers, does not represent the bulk mass of disks. What about we directly study the gas, which is a dominant mass component? And using that information, if we can have a significant sample, we can start to test different evolution mechanisms. So this is a simple example showing you can use how the gas disk mass and the gas disk size evolve over time to test the leading theory, the disk wind and the viscous evolution. So that was the motivation of AgePro, the ALMA survey of gas evolution in protoplanetary disk. So our goal to trace the evolution of gas disk mass and size throughout the lifetime of protoplanetary disks. So this is our team. We have 4 PI teams and about 25 people in total. So what I'm presenting today is really the result of a huge effort from everyone in the team, particularly the younger generation, our postdocs and graduate students that really did the heavy lifting work. Okay, so for this program, we selected 30 disks to study 0.1 to 6 million year old disks. Because the individual star's age is highly uncertain, so instead of focus on individual source, we focus on 3 groups. So selected from Ophiuchus region to represent the less than 1 million year disk. We selected class 1 and the flat spectral sources from this younger region. And Lupus class 2 disk represent 1 to 3 million year, and upper score 2 to 6 million years. You can see the HR diagram distribution compared to evolutionary tracks. So it's hard to decide the individual age very accurately, but we're focused on the systematic offset of the 3 regions in terms of their age. So we focus on stars with spectral type M3 to K6, particularly roughly corresponding to 0.3 to 0.8 solar mass stars. So choosing this age, you're trying to narrow down the effect of evolution itself rather than the effect of stellar mass. And we focus on single or wide separation binaries to avoid any known tidal interactions between close binaries. And the sources are selected from previous shallow surveys with some gas indications. Okay. So one of the primary goals is to measure the gas disk mass. So how we do this? Because traditionally in molecular cloud, the gas mass tracer is usually you use the dust either from extinction or millimeter emission and do a conversion based on the gas to dust ratio. Or you use carbon monoxide, which has a classic ratio to H2 about 10 to minus 4. But those tracers may not be the sanely reliable for protoplanetary disk. So for example, millimeter continuous emissions, so you have to consider the dust opacity. As dust are growing in protoplanetary disk, the opacity may change over time. More importantly, the gas to dust ratio are expected to change over time. So continuous emission may not be an accurate tracer of the bulk gas disk mass. Also, the classic idea about using carbon monoxide, using this canonic ratio of 10 to minus 4 to convert to gas mass, it also seems to be problematic based on recent studies. So this is an example showing with a small number of disks at different ages how the CO abundance change over time. So you can see in the youngest population for disks less than 1 million year, their CO abundance are consistent with interstellar medium value 10⁻⁴. But when you go to older and older disk, there is a very wide spread, 2 orders of magnitude spread, and also the older one seems to be more depleted in compared to the IMSM ratio in terms of the CO abundance. So how do we do this? Instead of just relying on CO itself, we added an additional tracer, N2H+, to constrain the CO to H2 abundance ratio. So the usage of the N2H+ is because this ion is sensitive to the CO gas abundance. When CO gas is present, N2H+ can be easily destroyed to form HCO+. So N2H+ can only be abundant in the CO poor gas. Also, the N2H+'s formation is also competition of N2 and CO. They compete for H3+. So when CO is abundant, it limits the formation of N2H+. So both the destruction and the formation pathway suggest N2H+ is only abundant in the CO poor gas. Of course, this is theoretical. You have to do some comparison with real observations. So this is a prediction of N2H+ to C18O line flux ratio, how it may change with the different CO to H2 ratio in the gas. So you can see this ratio is correlated with the CO to H2 abundance ratio in gas very well, theoretically. And then we did the benchmark test. With 3 disks, they all have HD detections from Herschel. And so far, HD has been mostly reliable gas mass tracer. So this is our benchmark test. So we take the C18O line flux of those 3 disks, TW-Haya, DM-Tau, Gamma Yuga, and do the traditional way of using CO gas mass and convert to H2 mass. But now, because of the CO has 2 orders of magnitude uncertainty in their abundance, so you see those colored dots are the all possible range of the gas disk mass. But instead of just using CO, we now added N2H+, which is the orange box here. So you can see N2H+ dramatically shrinks the possible range of the gas disk mass. And the gray color here is the constraint from HD 1 to 0 line. So you can see orange box in generally consistent with the HD measurement pretty well. So this gives us a way to measure gas disk mass in a population of disks. Okay, so that's what we did for the H-Pro program. So this example of the key science lines, we have continued from ALMA observations, and we have 12 CO 2-to-1 line, which we use to measure the CO gas disk size. So that gives us the size. And then we use 2 CO isotope logs, 13CO, C18O, and N2H+ to constrain the gas disk mass. So those are the key science lines for the H-Pro program. We also have other molecular lines in the setup as serendipitous studies. So all of the data have been taken and processed, and papers are submitted, and hopefully all the results will be coming in a month. So this is our 30 disks, millimeter continuum, and the 12 CO lines. For the Ophiuchus regions, you can see the 12 CO is heavily contaminated because it has still envelope and outflow materials. But for the class 2 disks, the 12 CO generally looks pretty good. There is a couple of sources, there may have some cloud contamination. But down to 13 CO and the C18O, they look very clean. From the H-Pro program, for the first group of results, we have 12 papers, including an overview paper to explain the design of the program and highlight some key science results. And then we have 3 papers to focus on the 3 star-forming regions to see what are the statistics we see in each regions. And we have 3 papers to explain how we measure the gas disk mass, dust substructure by visibility fitting, and the gas disk size. We have 3 theory papers trying to put HPRO results, the measurement of gas dust properties, into current theory. So in particular, we compare our dust observations with dust involution models, and we take our gas disk size and mass measurement compared with 2 population synthesized models, the viscous turbulent involution versus MHD disk wind. And the third one is we considering the impact of external photoevaporations, so the environmental effect on disk involution. And finally, we have 2 additional papers showing the beautiful surprise in the HPRO observations. One is there is a disk which shows hint of circumplanetary disk, and the other one is a disk which show order of magnitude changes in its millimeter continuous flux in the time scale of hours. Okay, so let's give you a few highlights of the key results. First of all, it's the gas disk mass is one of our main goals to study with HPRO. So as I mentioned, we use CO isotope log lines and intertruss. So we will the goal is to integrate the information from those line fluxes and compare with a large grade of thermo-chemical model and to see what is the best fitting gas disk size, gas disk mass, and the CO abundance. So using those line fluxes and also the 12 CO line emission sizes, which give us an idea about how compact the disk is. So we compare those results with a large model grade, over 3,000 thermo-chemical models, and do a Monte Carlo Markov chain search to estimate the posterior of the gas mass distribution and the CO abundance. So this is an example about the results. So this is the result for the gas disk mass of the 3 star-forming regions. So the gray color is our Ophiuchus sample, and the gold one is lupus, middle age, and the teal one is the upper skull region. So on the right is the median value of the 3 star-forming regions. So interestingly, the youngest star-forming region has a median mass close to the minimum solar nebula, then the most massive, and it quickly decreases by almost order of magnitude when it's at the middle age. And the most surprising thing is when we look at the lupus and upper skull, which upper skull is significantly older, we don't see significant decrease in the gas disk mass. So this, which also checks the line flux to make sure this is not some caveats in the model. So when you look at the millimeter flux of the 2 samples, so lupus and upper skull, you see those are separated 2 samples. You can see it's offset here. So this is a cumulative distribution of the continuous flux. But when you look at the line observations from 12CO, 13CO, C18O, if you exclude the one source in lupus region, and you find the distribution are pretty similar across the 2 regions. So suggesting whatever model you use to measure the gas disk mass, because those line tracers give you very similar flux distribution, you ended up with those gas mass across the 2 regions will be similar. Okay, so yeah, so this is a continuous versus C18O flux. You can see the continuous has an offset among the 2 regions, but the C18O flux are covering a very similar range. Similarly, NH plus, you see the NH plus from the two regions are very similar. So this was a bit unexpected because we were thinking maybe the upper school region would have a lower gas disk mass compared to the younger regions. So this is putting things together. So this is the dust mass from individual source and from medium value across the three regions. You see the dust disk mass seems to decrease over time. That's already well known from previous millimeter continuous survey. When we put the gas disk mass on the map, you will see it shows a different pattern. So the gas disk size mass first decrease by 1 order of magnitude from the ophiuchus to lupus region, but then lupus and upper skull are very similar. So this interesting pattern led to a swing in the gas to dust mass ratio. It started with a median value close to 100 as we expected. But then in the lupus region, because the gas mass decrease is faster than the dust mass decrease, so the lupus region has a lower gas to dust mass ratio on the order of 40 in the median. But back to upper skull, you can see here, the dust mass decreases, but the gas mass is similar to lupus. So its gas to dust mass ratio increase, so goes back to 100. So this was not realized before. Traditionally, planet formation is thinking the gas to dust ratio will monotonically decrease over time. So this is something we were not expecting. Secondly is about the gas disk size. So for the embedded sample, we are doing to measure the velocity gradient to see where the inflow velocity convert to the Keplerian rotation to look at the transition radius. So this work is still in prep. For the first group of results, we mainly publish the class 2 disks. So these gas disk sizes are measured as 90% of the flags from the 12 CO line emission. So we find that most of the disks are rather small. So you can see the dust disk versus the gas disks in our sample. So most of our gas disks are within 100 AU. So with lupus, the medium size is 75 AU and upper skull is about 100 AU. So this is much smaller compared to many other well-studied disks. Like iron loop, it extends to 1000 AU. So this suggesting for the typical population, the gas disk is not that large. It's on the order of 100 AU. Okay, so how we put the gas disk mass and the size into the expectation of disk evolution. Before we put that, this is showing how all the measurement properties in our sample changes with age. So the 3 star forming region improve, suggesting young, middle age, and older disks. Their dust disk mass seems to be decreasing over time, while the gas disk mass you see first fast decrease and then slows down. And the dust disk size, we don't see much evolution. So the 3 star forming region seems to be similar. And the gas disk size is also similar in the lupus and upper skull. Upper skull may be slightly larger. And the ratio gas to dust disk size ratio is on the order of 3 in the medium. And then the CO abundance, we see CO is significantly depleted compared to ISM level, so 10 to minus 4. But lupus and upper skull look similar. And the spectral index is comparing 2 millimeter continue, so band 7 and band 6 in ALMA. So you can see Upper school has a larger spectral index compared to lupus, although there is a wide spread, suggesting in the outer disk of upper school regions, the dust particles are smaller compared to the emission region of lupus. So we have theoretical works to trying to put those results into context. One is dust evolution. So this is a work done by postdoc Nicholas Katovic and Matthias. So what they did is rerun an extensive grid of dust plus viscous gas evolution models up to 10 million years with a wide range of stellar and disk properties, and in particular trying to mark different dust traps mechanisms due to, for example, different masses of planets. So this is a strong case with Jupiter mass planets making gaps inside the disk, and outside of their edge, they can accumulate dust particles. And with those simulations, they then run simulated ALMA observation to see what the disk continual flux and the disk size would look like in different cases of pressure traps. And then they compared their continual flux from models at different ages, different stellar masses with our observations. So I know it's a busy plot. Let's look at the bottom first. So this is showing different stellar mass and the continual flux. So this is showing a different fraction of disk mass as a fraction of stellar mass, so different initial conditions. And different columns showing from the younger age to the older age. So you can think about how the disk continual flux will evolve over time. So from the youngest stage, the disk I expect to be bright, and then the millimeter flux will decrease over time. So how quickly they decrease over time depends on if there are any pressure traps in the disk. So the bottom panel showing you if there is no pressure trap at all, how the millimeter flux will decrease. So it decreases the fast. And if there are some weak pressure trap like Neptune-sized planet inside the disk, and it will slow down the inward draft and keeps outer disk still have some millimeter continual fluxes. You can decrease slower. And if you have a strong pressure trap like Jupiter mass planet, and it's the slowest, can keep still significant amount of dust particle in the outer regions. So in our result, it seems to suggest the pure no pressure trap at all draft is the decrease is too fast, inconsistent with our observations. It's more consistent with a weak or strong pressure trap. And they also compared with the spectral index from our measurement with their simulations. So this is an indicator of the dust particles left, their sizes in the emitting region. Again, if no pressure trap, so you see the spectral index goes to larger and larger, indicating smaller particles in the outer region, because most of the larger particle would have drifted inwards. So you can see this, particularly this case, is inconsistent with our observations. And with the weak or strong pressure traps, those are better consistent with our observations. In particularly, the weak pressure trap seems to have the better match with observations. Of course, one of the main goals is to study what mechanism drives the gas disk evolution. So this is the work we tried to compare with disk population models under different evolution mechanisms with our observation. So this work is led by Benoit Talbot. So he uses two mechanisms to model disk population. One is viscous disk plus internal photoevaporation. Another mechanism is MHD disk wind. So he started with random initial conditions and the parameterization of the two mechanisms and let the population evolve, and then look at the involved population, their distribution of gas disk mass, gas disk size, disk fractions with infrared access, and accretion rate. So those are the four observable constraints. One is disk involution, the near infrared access of disk fraction. So it decreases over time. And so the accretion rate of different star forming regions. So those are individual points, the median value. And the last two constraints are from HPRO directly, our measurement of the gas disk size and the gas disk mass. So the individual points and the median value from our observation constraints. So his model shows he could use a particular parameter range of MHD disk model to reproduce the bulk properties of in our observation in terms of disk mass, disk size, and the accretion rate. But he's having a great difficulty to use the viscous and the photoevaporation model to match all the bulk properties. In particularly, if we match the disk fraction, disk accretion rate, and the CO gas disk size, the best model would overpredict, which is the gray line here, overpredict the gas disk mass by nearly order of magnitude compared to our observations. And this is the probability distribution in his model, the background gray color, and the red dots are our observations in terms of the disk mass and accretion rate distribution. So you can see the MHD disk wind population roughly covers within 90% of the population covers what we see in HPRO. While with the turbulence case, it has a lot more outliers, which beyond the 90% population. So in general, the MHD disk wind does a better job in reproducing what we see in the HPRO population. So this is a particular science case. PRIMA will do much better. So because PRIMA will observe HD 120 line, which is a more accurate gas mass tracer in 200 disks and covers a wide range of evolution stage and will enable a great population study. Finally, for the last few minutes, I wanted to quickly talk about some follow-up project we do for the HPRO sample. So one particular thing is now we are combining the gas disk property we study with ALMA with JWST for the same sample. So we have cycle 2 program to study the HPRO sample to study their inner disk chemical tracers. With JWST MIRI, you can detect water and organics in this wavelength range, which traces the inner few AU of protoplanetary disks. With this sample, we wanted to study how the volatile budget, water, and organics in the terrestrial planet forming region, how it evolved over disk lifetime. And also if there are any indication of pebble drift would bring extra volatiles to the inner disk. So we have gotten all of the data now, so the results looks pretty promising. If you just look at the raw data, so those different colors showing example disk spectra from the 3 star forming regions, you see significant difference across the 3 regions. For the embedded samples, we see molecular lines, but also ice absorption features, probably from the envelope materials. and the class 2 middle age sources with the abundant water and organics. When we look at the upper scores, you can see the spectrum looks much cleaner in terms of, because it's weak, very weak water or no water at all. You take the individual waterline flags, you see clear offset across the 3 regions. So this is very preliminary. We are still looking into the analysis. What this really means is this due to the stellar luminosity, the accretion rates, but there are significant water luminosity across the 3 regions. And also we notice in the oldest region, the upper score, it seems to be more organic rich compared to the younger regions. So this example of one of the upper score sources. You can see C2H2, C2H2, HCN, and other organic molecules. Another thing we noticed in this sample is the embedded disk, the younger population, compared to the middle-aged ones, there seems to be lack of CO2 features, which is quite prominent in many of the class 2 disks. You see here this feature, but in the younger population, the class 1 sources, they have shown very little awake CO2 features at all. This is interesting because this is actually consistent with the prediction of current pebble draft theory. So if no pressure trap inside the disk, most of the pebble will draft into the inner 1 AU region within 1 million years. So you have the highest pebble flux in the first 1 million years. And because the water snowline is closer to 1 AU compared to the CO2 snowline, so current pebble draft model predict at 1 AU location, there should be an interesting low, so CO2 poor, water rich phase within 1 million years. So this is indeed consistent with what we are seeing in this small sample of young disks, the lack of CO2 features. So based on those initial results, we proposed to study a large survey of Protoplanetary embedded disk in Ophiuchus region. So we study class 1 and a flat spectral sources of 40 disks in the Ophiuchus region. So this sample will help us understand the first 1 million years of chemistry in the inner Ophiuchus AU and whether pebble draft can make a significant difference. So this is our sample. So this in the blue is what we are going to observe in the next 1 year. And the sources we already know their substructure in the outer disk at the 5 to 10 AU scale. So this will bring the statistics, say the outer disk pressure trap condition and the inner disk chemistry. Firstly, for the first 1 million year. Okay, so this is the last take-home messages. AgePro is the first systematic ALMA program to trace gas evolution in protoplanetary disks. The most surprising things for us is we find the gas and dust seems to involve at different time scales. Particularly, you are seeing this gas to dust mass ratio involve over time have this interesting swing. And compared with population synthesized models, MHD disk vein seems to reproduce the evolution better. The viscous model in particular having difficult to over predict the gas disk mass when matching the other bulk properties. And for the next few years, there will be great synergies between ALMA and JWST to study the disk chemistry, how they may be impacted by the outer disk properties. And in the 10-year timescale, I hope PRIMA can give us a much better population study to understand the disk evolution and their water budget over protoplanetary disks. Yeah, thanks, that's all.
Wonderful. Thank you so much. We can go ahead and take questions. So I'm happy to start. I was wondering if you would tell us a little bit more about the variable source that you had found in Age Pro.
Yeah, so that source is an upper score source. We observed it with several execution blocks. So each execution block is like 2 hours. So in one night, the source decreased, the flux decreased by factor of 9 in a couple of hours. We were really surprised, but those observations were taken in cluster, so there are other sources taken at the same time with the same calibrator. All the other sources look normal, so the continuous flux were constant. Only this source varied. And a few days later, it was observed again and seems the flux still decreasing, but now it's more or less stable. So we suspect that there was a flare in the continuous flux. Also, when we compare the line flux, it looks constant across different executions. So it's just the continue. Our proposed hypothesis is this disk, its center probably has a binary source, and when the two sources are very close to each other, they could have their magnetic field touch with each other, so have the magnetic field reconnection and generate a flare. So we have been trying to get optical follow-up and keep with ALMA monitoring, but it's very hard to get done.
So are you suggesting this is a synchrotron emission source if it's magnetic fields? Like what is the emission mechanism?
Yeah, synchrotron emission.
Okay.
Yeah.
Very cool. Thank you. So we have a question in the chat from Neil Turner. And he asks what links between water vapor and water ice could potentially be probed with PRIMA?
Yeah, that's a great question. So there is a water ice feature at 43 microns, so give us some handle about the water ice abundance. And we would also use the water vapor to know the gas phase water. I think that's give us an interesting constraint on the where the ice reservoir is mainly what type of dust particles would carry water ice. So basically, the vapor to ice ratio and also the rock to ice ratios. We can try to see if the different regions we predict with models whether they are consistent with PRIMA observations and what disk properties produce different ice to rock ratios, gas water vapor to ice ratios.
Thank you. So again, feel free to raise your hand, speak out, or put your question in the chat. Right, we have a question from Jason Glenn. So Jason asks, could polarimetry with ALMA inform your interpretation of a magnetic reconnection cause of the flare?
That's an interesting question. I haven't thought about it. So the pattern is we don't know the flares period. So there are some K2 observations suggest it may have some like a 10 days period for the continual the optical continual flux variation. But we haven't not been able to do follow up. Yeah, but I think the polarimetry is interesting. We'll have to see if the signal to noise ratio will be enough.
Thank you. All right, we have a question from Hendrik Lins. So Hendrik asks, does an increased external radiation field, like perhaps that present in upper SCO, could this enhance the efficiency of the disk winds?
Yeah, so that's a great question. So as I mentioned, one of our paper is to look at the external UV radiation field, how they impact upper SCO. So in terms of the G naught value, so the medium G naught for the surrounding environment for lupus is around 3, and upper SCO for our sample is around 10, so slightly higher. So we did a test. We find at this G naught level on the order of 10, so it has some impact on the gas disk size. So the disk will be smaller, slightly smaller, compared to if the G naught is on the order of 1. But for the gas disk mass impact on this G naught level, it's pretty small, negligible.
Thank you. All right, we have another question from Neil Turner. So Neil asks, are centimeter wavelength radio observations feasible for the flaring source?
So it's in upper SCO. So if you want to use VLA, it's pretty low deck. Maybe on the borderline possible, yeah, but it's challenging to do the observation at longer wavelengths.
So Neil mentions there were detections of polarized 6 centimeter emission from T-tau S, or sorry, maybe that's the I think T-tau S source years ago by Tom Ray et al.
Yeah, so I think there are a couple of known millimeter variability sources, and in the paper we're trying to compare our change of amplitude. It seems our source is like in the middle, not the very extreme ones. Yeah, I think we could try to. It just we have been trying for the past 2 cycles to convince the tech to give us some time to follow up on this. But yeah, for single source observation, it's challenging to convince.
Well, we all seem very interested, so I hope you have better luck this cycle.
Yeah, thanks for the support. Yeah, I could not see any of the questions. Is that on a separate channel? Or?
There's a chat on Teams. Should be a button that's available at the top.
Oh, okay, I see.
Yes. All right, so if there are no more questions, I'd like to thank Coco again for a wonderful talk, and thank you all for attending, and we hope to see you next month.